working at ARM in the Okay. Hello, everybody. I hope you can hear me. I am Tamás Bám, working at ARM in the open source software group, and here is my colleague as well.
Hi, I'm Rafe Coles. I also work in the open source software group on the Trusted Firmware M project.
In the last 4 years, I have been working on the Trusted Firmware M project. One of my focus areas was the secure bootloaders. Along these years, I have recognized the fact that not only the software vulnerability is the only way how a system can be hacked. The security of a system, even without an exploitable software bug, can be defeated by physical attacks. Today, we are going to talk about the physical attacks, corresponding software mitigation techniques, and what have been improved in our project regarding this topic. The short agenda for today. First, a quick overview of the physical attacks. What are these, how to perform them, the effects on the code execution. Then a generic overview of the software countermeasures. How can the code be written in a way to be more robust against physical attacks? Then we are going to talk about the MCUboot and Tfm projects, what enhancements was implemented in these. Finally, we are going to introduce an in-house developed fault injection test environment based on the QEMU emulator. A physical attack is when an attacker deliberately changes the expected behavior of a circuit. To achieve this, the device is moved out from its tested and proved operational conditions to force the hardware to a stage when might random hazards appear. There are many ways to do so. The chip can be heated up or even cooled down over the tested temperature range. The stability and accuracy of the input signals like power supply and clock signals can be changed easily with an external device connected to the input pins. More advanced attack could be to shoot the surface of the chip either with an electromagnetic pulse or a laser beam. All these attacks have different effects. On the right-hand side, there is a figure to explain the change on a circuit level, how can affect the microarchitectural behavior of the chip. For example, it can affect the instruction fetch or decode, the data fetch or store, or might change the content of a register. As a result of these changes, the code execution will be changed at the highest level. And actually, this is the ultimate goal of the attacker. He wants to derail the expected execution of the code to some unknown random direction which might be beneficial for him to break in a system. As I said, the physical attacks cause a random fault in the hardware. What actually happens strongly depends on the actual hardware. So from the attacker point of view, the execution of the physical attack is a try and fail loop, until in some cases the attacker finally finds the right parameters of the attack, like the type, location, timing, which at the end make the attack successful. Now let's talk about what kind of faults are observable on the code execution level. The most common ones are the instruction skip and the register corruption. Instruction skip means that few machine instructions is not executed by the core which normally should be. It can cause that a variable is not updated or a function is not called, or in case of conditional check, the wrong branch is taken. Another frequent fault type is the register corruption. This means that the value of register changes in a random way, a single or multiple bits flip. It can have various effects on the code execution, like branching to a different address, or read or store data to modify addresses. But even the function call parameters, including the input and the output ones, can be tempered since these are passed through registers. The implemented software countermeasures and the test environment are also focusing on these. Sorry. Software countermeasures are meant to make the code more resistant to the effects of the physical attack. The goal is to not fix the effect of the attack, instead just recognize that something unusual happened in the control or the data flow. If such a situation is recognized, then the software must take an appropriate action, usually to hang up the code execution and go to some error handling routine, like an infinite loop, reset the device, or even clear device secrets. Of course, the software countermeasures is not the only way to protect against physical attacks. There are dedicated hardware components that serve the same goal. The best approach is the combination of these, the hardware and software countermeasures, and applying both. But even in this case, they are not providing full protection, just significantly decrease the probability of a successful attack. So far, we have covered what is a physical attacks. Now let's see what can be done in the code to protect against them. General advice is to pick up constants for return values which have a complex bit pattern and have a big Hamming distance between them to make it harder to change from one valid value to another with a bit flip. Some of the countermeasures are built on some constraints of the attack. The timing of a single attack can be accurately set, but time to attack precisely, which are very close to each other in time, is hard. There is a high probability that one of the attacks will fail, so making important operations redundant helps to recognize the attack. Double checks serves exactly this purpose. Important condition checks could be a good target for an attacker. In order to recognize an ongoing attack, it is recommended to duplicate the important combination checks and might the variables as well which hold critical data. In case of inconsistency, the software can act accordingly. Another effect of a physical attack can be an early exit from a loop operation without completing it. In a cryptographic algorithm, this can weaken the strength of a crypto encryption or digital signature. In the end, this weakening can be used to reveal the secret key. So a good practice is to check the value of the loop counter at the end of the loop against its expected value to make sure that the loop is really completed. The flow monitor is meant to recognize an unexpected turn in the control flow. For example, a function call is skipped as a result of an instruction skip. The flow monitor is a global variable whose value is adjusted time to time as a program execution is progressing, and it is checked against an expected value. If it is not matching, then the control flow was not correct. For more details, I recommend checking the links in the slide. There are many resources available on the internet about how to perform a physical attack, explaining the exact steps and necessary devices to make it possible to replicate the attack. Offensive devices can be built for a low cost, but even there are commercial tools that are meant to perform physical attacks. These are delivered with a software framework to make the execution of the attack faster and easier. However, on the protection side, there is less free content, mainly just research papers. Of course, there are certified products against physical attacks, but these are commercial products and contain proprietary code. Before we started the implementation, we have done a research to find an open source implementation that could be reused. There was one project, but it was not major enough to use. So we decided to make an open source implementation in pure C to make it free and portable. Of course, the protection on the C code level doesn't provide any guarantee that is really working in practice. Actually, the compiled code what is really matters, and it depends on many things like the CPU architecture, the compiler, the level of optimization. So always the compiled code must be verified with visual inspection and with testing. That is why we also developed a fault injection test environment that can simulate the most common faults like instruction skip and register corruption. There are many resources. The Trusted Firmware M project has two major parts. One is the secure runtime environment, and the other one is the secure boot process. The default secure bootloader in TFM is the MCUboot. If an attacker managed to bypass the secure boot process, that he can execute an arbitrary code on the highest privilege level. This can lead to steal the device secrets like cryptographic keys, credentials, sensitive user data. So the bootloader is a target that promises a big profit if the attack is successful. Another property of the bootloader which makes it attractive for an attacker that it has a time-deterministic behavior. It has a constant time execution and all the operation happens exactly the same time. So there is plenty of time to improve the attack vector. At the bottom of the slide, there is a small code snippet from MCUboot. If you are not considering the physical attacks, then this is perfectly fine. But when fault injection comes to the picture, then there are many vulnerable parts. Instruction skip could lead that the main verification function is not called at all. Other option is that with the register corruption, the verification function's return value is getting modified. even execution is trapped in an infinite loop, attacker can try to break out and continue the booting. This can be done with instruction skip because the infinite loop is a single branch instruction to its own address. MCUboot is a secure bootloader for 32-bit microcontrollers. It supports many digital signatures, types, and also encrypted images. On this figure, you can see its architecture. There is a generic boot and update logic, which defines an abstraction layer to hide the device-specific details. The crypto operations are provided by external crypto libraries, which are also accessed through an abstraction layer from the generic boot logic. We have focused on the generic boot logic in terms of physical attacks. We inspected and hardened the code flow, which are crucial from the device security point of view. This means that we have looked for sections of the code where an injected fault in the code execution could lead to bypass the secure boot process and boot in successfully an image with an invalid signature. But we have not touched the crypto libraries since they are independent projects from MCUboot. So the crypto libraries still can have vulnerable sections of code from physical attack point of view. The level of provided protection by the crypto library needs to be checked with the corresponding project. So just a heads up that these enhancements are not extending the entire bootloader software stack. On this figure, you can see the main boot flow. In the middle with yellow, there is the generic boot logic, which was in our focus. Our goal was to not entirely rewrite the MCUboot code, instead just provide a library which can be optionally enabled at compile time, and in this way make the boot flow more robust. We wanted to preserve the original code as much as we can, because not all the product requires protection against physical attacks. It depends on the threat model of the device. We achieved this approach with implementing the previously mentioned countermeasures in a way that they are wrapping around the crucial function calls and condition checks to make possible that the side effects of a physical attack are noticeable and the software can go to an error handling routine. This tiny wrapper layer is represented by the orange boxes around the yellow ones.
So the second half of the talk is roughly about what we produced. So this is split into roughly 4 categories. Firstly, we have the library, which is a generic implementation of the countermeasures that Tamas mentioned earlier. There's no novel countermeasures in here. We're just doing sort of nice implementations of the standard ones. And then the second thing we've produced was a verification tool. So this allows us to actually verify that the countermeasures are correct. And then the last 2 things are so these 2, the library and the tool, have been upstreamed to MCUboot. The tool is now run in the MCUboot CI. And then the last 2 things are to apply this work to TFM. So the application to TFM is the same library, just used in TFM. And then we have another version of the tool that was used for testing TFM. Next slide. So the countermeasures in MCUboot are, as I said before, just the standard countermeasures. You can see them listed at the bottom. One of the things that we really wanted to focus on here was integration, the ease of integration. So one of the key priorities for MCUboot was size. It's used in ROM a lot of the time, and you don't have much space. So we've split the countermeasures into multiple different profiles. So this means that the person integrating it can pick how much protection that they want. Because some of these things, like the double checks, are literally doubling the size of code that you're producing, at least for the checks. So they have quite a big impact on code size and a slightly smaller impact on performance. So the profiles are a good way of splitting things up so that we've got minimal, so that people can choose the amount of protection that they wanted. Next slide. So because this was going into an open source project, we have more limitations than most of the other implementations of this. So a lot of the time when you're producing a product that is hardened against fault injection, a lot of the mitigations will be done in assembly, or alternatively, they'll be done in C. But because the actual mitigations are as a result of what assembly gets executed. You still care about the generated assembly. So they will mandate that a particular compiler has to be used. They'll mandate a compiler version has to be used. And we can't really do that. Because it's open source, we don't know what compilers people are going to use. We don't know what compiler versions people are going to use. We actually don't know what ISA it's going to be compiled into. So we had to write everything in C, which does come with some downsides. The main one being that it's quite hard to check that you're actually producing correct countermeasures, because you don't know what the compiler will produce from the C. You can do reasonably well with this by messing with the C by messing with some of the features of the C language, like volatile, to prevent compilers, to basically force compilers to do what you want, because volatile prevents optimization and allows you to get away with a lot of things that otherwise would be marked as obvious duplicates of dead code. So C gives us a bunch of benefits. The other one is that it's really easy to integrate with. So what we basically produced was a couple of drop-in replacement macros. So all the vulnerable areas will just have a macro that you can replace your code with that sort of wraps around it. And this means that the effort to actually integrate the library is very minimal. And the other thing we did for portability, again, was put lots of effort into minimizing the code size. So we've got all these profiles and they are implemented with macros. So you can just toggle off all of the countermeasures if you want, and you'll be left with effectively the same code as the original. All of the types will be restored to standard, and all of the conditions will go back to how you'd expect them to be. Next slide. So on the left, you can see there's the original MCUboot code, and on the bottom left, you can see that there's the hardened code. So you see there's a few things here. There's FH call is our wraparound function calls, which does some setup at the start and tear down at the end, which is basically the flow control, the state monitoring that Tamas mentioned. So it saves the state at the start and then checks that the state is the expected one at the end. So that checks that the function actually gets called. We've got some labeling in there as well for the testing tool that I'll talk about in a second. We've got an updated equality function, which this is used with the double checks. So it will run the equality test twice. And if you have the other thing we've got is doubled variables. So each variable becomes a tuple with the original value and then the masked value, which is derived from the original value by XORing it with a mask. And then we can check that the original values and the masked values are XORed between each other. So we can check the integrity of a single variable. And then we can also do this double check by checking the masked values are the same as the original values, which gives us a double check for everything. And the other thing we've got here is FH panic, which I haven't expanded, but this is a slightly harder boot failure loop. So it just contains a very large amount of branch instructions. So it's harder to skip out of the loop because you'll just be returned to the start. I think there's about 9 branch instructions in that. Next slide. So the countermeasure performance actually turned out to be quite good. The profiles help with minimizing code size, but even at the top end, it's 2.6K. So that's not a huge amount for hardening the whole bootloader compared to the rest of it. And then at the lower end, it was, 250 bytes with it disabled. So that's really quite reasonable. And I think that really helped with getting it merged into the project, because no one could complain that we were vastly increasing the code size for questionable benefits. And the actual performance of the thing, these results were generated with the tool, which again, I'll talk about in a second, but the performance is really quite good. It looks like we have the countermeasures do work, and the profiles all provide more protection than the other one. So it does look like this has basically been a success. Next slide. So the testing tool, the important thing that we spotted here was that all of the faults that we were looking at could be modeled using a standard debugger. So you can do skip faults by incrementing the program counter, and you can set registers to random values. And once we knew that, it was very easy to build this tool, because effectively we're just getting a platform you can run in CI, which was QEMU in this case. And then we just had a script which controlled the debugger, and then would run faults using that, and we'd sort of do faults on areas that we suspected faults would be were suspected that faults would cause problems as labeled by the countermeasures code. And the trick here was that we could really easily evaluate whether a fault had succeeded or not, because we would just give MCUboot an invalid image, and if the invalid image booted, then we knew that our fault had successfully bypassed the protection. Next slide. So the second thing to do was to implement these countermeasures in the Tfm runtime. This is ongoing, but it's using all the same libraries, all the same code. The only tricky bit is that the Tfm runtime is slightly larger, so it takes a little bit more time to go and replace all these calls with FIH call, etc. But at the moment, it's doing reasonably well, and the generic implementation is holding up. So that's nice that basically it does look like our thing is usable in multiple contexts, which was one of the aims, is to provide something that is basically an off-the-shelf solution that you can just pull out and put in a project, and it will provide some protection. Next slide. So the main challenge with porting it to TFM actually was the testing tool, because in MCUboot, we had this really nice way of telling if a fault has succeeded. And in TFM, it's much harder, so we had to rewrite the tool and make it a lot more complex. And the main aim was basically to allow it to scan memory, because the isolation hardware used to protect the secure side, we can see all the configuration of that in memory. So we have the debugger run through the program first to start with to check what all the values of the memory should be at a set of points, and then we will trigger faults, and then we'll compare these against the expected values. And it turns out that solves our problem in terms of trying to work out what a fault is. We've got to be a bit conservative here and say that any change to the isolation setup is a failure of our countermeasures, but when most of them actually would just cause the system to be inoperable, but better safe than sorry. And this also, while we were doing this required doing a lot of rewriting the tool. So we've got lots of nice features, including a much better Python layer to write tests in. We've got QEMU save loading support, which meant that we could restore the state of the code. So we could then skip backwards and we could run lots more tests, because that was our main limiting factor, is that you can run, the more tests you can run, the better your coverage is, but it was just taking quite a while to run the tests, which has now got a lot better. And then we've got some quite nice machine parsable output in JSON. And yeah, I think that is roughly everything that we implemented. Next slide.
Yeah, so far we only relied on our simulator environment to test the implementation, but it is in our interest to get external feedback as well from experts in this area. So recently ARM has started an internship whose goal is to do an external verification of the hardened MCUboot code. And this is done in a collaboration with ARM and the Sorbonne University. During this internship, the testing will be done in a different simulator environment and based on the progress made on a real hardware test bench. The result of the validation could be used to enhance further the code quality and make MCUboot more secure. The result is going to be available in the third quarter of this year. And this is our last slide. We have just collected all the links from the presentation. So thanks for your attention and time. And I think we have 1 minute for the questions.
Yeah, so we can quickly go through. There's a question about whether it's possible to instrument compilers to add checks. This is something that lots of people are looking into because it's a much easier way of doing it than the C. But at the moment, I don't believe anyone has actually produced any usable compilers. There's lots of research going on with universities, but no one has produced anything that has been upstreamed yet. Unfortunately, because it would be a lot easier if we could do this in the compiler. I'm not sure we're going to get to the rest of the questions. We'll go and answer them in chat later, but probably the end of the session. Yeah, it's a good idea. Okay. Thank you very much for your attention.
Thanks, Rafe and Tomasz, for your interesting session. And thanks for those who attended, and we look forward to further interactions.